for his keynote. So while Tushar is gonna set up, I'm gonna introduce him, and I'm gonna let you know about his very lengthy career, very successful career. So Tushar Krishna is an associate professor in the School of Electrical and Computer Engineering at Georgia. He also serves as an associate director for the Center for Research into Novel Computing Hierarchies. And he also held the ON Semiconductor junior professorship between 2019 and 2021. Has received his Ph.D. From M.I.T. And he's doing Georgia Tech. He worked, we all know things due for every calculator on Tuesday, so make sure to follow up with that. He works on computer architecture, interconnection networks, and network concepts, and deep learning accelerators. A lot of focus has been on optimizing more computing systems, and his research has received several awards and funding from multiple agencies like NSF, DARPA, and also lots of industry like Intel, Google, Facebook, and others. He has received several awards, including topics from computer architecture, actually 4 Best Paper Awards. He's already in the Hall of Fame of HCCA, and he has received many other awards from Georgia Tech as well. So with that, Tushar, please take it away.
I should be on my screen or
yeah.
Yes. And no audio, so no echo here. That's good. Can people on Zoom just ask if they can hear me?
Yes, works very well.
And if somebody else can check Zoom. Oh, very good. Okay, perfect. All right. So thank you all for the introduction. Thank you, Dimitri, for the wonderful introduction. Thanks. This is actually really a privilege to be here. I've kind of seen the profiles of, people who've given keynotes at this forum earlier, and I claim to be nowhere near their stature. So and again, welcome to all of you who are here in person and those of you who are online. So I'm going to talk about, just my journey, which has not been, as I said, very, very long, but I was, just like you all in about 15 years ago. And I'm going to talk about this general view of, doing research that goes beyond your own data. And so this talk is really about my journey, what I learned through the collaborations along the way. And I'll kind of just briefly walk through a timeline of where I'm at. So I actually did my undergrad in India at IIT Delhi. This was in electrical engineering. And I came to the US in 2007. I started my PhD at Princeton. And I actually was there for 2 years before my advisor transferred to MIT. And so my whole group with her moved to MIT in 2009. And so I spent the rest of my grad school career there, and I essentially graduated end of 2013 with a PhD from MIT in ECS. I actually joined industry right after that. I was always on the edge between industry versus academia. I was, I think, never very, very sure. And to be honest, I was really like intimidated by people like me who are now standing here, right? Like, how can I be a professor and give talks like this? That's really not me. So I decided to go to industry. Spent a year there. I think, joined at a time where I saw maybe the side of industry where, Intel was not really going through a very, very good phase at that moment. Our group kind of disbanded. People moved across to different areas and different companies. So that was the time I decided to actually then go on the academic market and really, give this a shot. So I spent a year at Intel. I actually went back to MIT for 6 months, just as the interim for a postdoc while I was interviewing. Then I started at Georgia Tech in 2015. So I've been there since I was an assistant professor. I got tenure a couple of years ago, and now I'm an associate professor there. So that's been kind of my journey so far. So as I said, it's been, a little bit of industry in terms of actually working there, but I've also collaborated extensively with industry through the last few years, right? So in terms of research areas, I think I really want to touch upon one of the things that I feel lucky that I've been able to do is, like, I've always been able to work on computer architecture plus a surrounding, area across the computing stack. So I've not gone very, wild yet in terms of very, very diverse areas, but just within the realm of computing, while I was in grad school, I worked a lot on architecture, but with relation to, circuits and EDA. While I was at Intel, I started looking at HPC workloads as well and trying to design specific accelerators for that. During my postdoc, we started looking at, again, circuits, the chip tape out, started looking at EDA. As a faculty member, I've kind of now delved into compilers, FPGAs, and also workloads, both machine learning and HPC. And over the last, I think, couple of years, started delving a lot more into systems as well, and also some emerging technologies. And in terms of industry interactions, like through grad school, I actually interned at AMD. So we've already, thanked AMD a few times. So I also have to thank them a lot for, shaping the initial part of my grad school journey. So I interned at AMD several times during my PhD, and a lot of my research was influenced with, ideas, interactions from them. I was at Intel, of course, started interacting with Intel researchers. A lot of my former colleagues from Intel moved to NVIDIA. So that kind of led to a stream of, collaboration with NVIDIA that are continuing to today. As a professor, I kind of started interacting a lot more with like other companies. So NVIDIA, Intel, ARM, more recently, like Facebook, Google, TSMC, like these are some of the more recent interactions I've had. And it's interesting, right? So some of these companies are definitely closer to technology. Some of them are like, cloud vendors, some of them are hardware vendors. So it's been an interesting learning experience interacting with researchers here and helping me shape my own journey as well. One of the things that I really want to mention is, so I think working on several of these areas with multiple collaborators has honestly allowed me to have an impact beyond the limits of my own expertise and time, right? So I actually do not claim to be an expert on a lot of the things I work on, but with these interactions, I've actually been able to do that. And that's something I kind of want to emphasize. So my key message today is actually is perhaps like is just expanding on my own style, right? So I think it's extremely valuable to focus on depth and breadth, right? So I really want to separate out your PhD thesis work, which is really depth, from your PhD journey, where I really want you to kind of embrace the breadth. And it's interesting, I was so before coming to Asplos, I spent a day in Seattle with one of my very close friends from graduate school. He's now a researcher at Amazon. And actually, he's mentioned something that I then actually put on this slide, right, is this topic. So he kind of was reminiscing about grad school and talking about how he wished he had done even more in terms of, expanding his technical and non-technical horizons in grad school, right? So that is something I really want to kind of emphasize, right? So there is, of course, your thesis work, your papers, but try to expand your horizons that through interactions in your school, through interactions at conferences. I'll also emphasize that, of course, we all go through imposter syndrome, so that's very natural, but you do not really need to be an expert on everything under the sun to carry out intelligent technical conversations and work on collaborative research, right? So this is something I've learned now. And again, as I mentioned, I used to be amazed at, my professors. And it's interesting now when I get sometimes, feedback from students when I teach the architecture course, they're like, oh, he knows about every topic in architecture. And I'm quite surprised when I read that, because I really don't. But I think as long as you have, your basic principles right, I think you can carry out a conversation, and that's really what you need, right? So of course, as again, re-emphasize this kind of the technical depth you need for doing cutting edge research, publishing at conferences like this. And there is the horizon about, collaborating, interacting, and, discussing ideas, for which you be open to that and do not really be scared. And I'll also mention that you'll often notice that sometimes a lot of side projects that you do end up actually having much higher impact than your main work. And that's certainly true for me. I think one of my most cited papers are not my first author papers. They're actually papers where I'm, second or third author. And that's really because of some of these interesting collaborations. I think that's something that, like, as I reflect, it's been a very, very interesting journey. And a lot of people have mentioned this in the past, you'll hear, but just kind of realizing this was very, very eye-opening for me as well. So if I go into the overview of my research today, this is, how I present my research. I say, hey, I work on, these large-scale ML systems. This is an example of a deep learning acceleration platform in data centers. These include customized chips for AI, call accelerators, NPUs, what have you, and they're often distributed. So you often have to scale the AI task, whether it's training or inference, across accelerators, right? So we look at designing these accelerators. We also look at designing the fabric connecting these accelerators. And fundamentally, the key challenge that my group and I focus on is the challenge of communication. So there's a lot of challenges in communication within AI systems, right? So there's the kinds of communication are really between the memory to the accelerator, between accelerators. The communication depends a lot on the workload itself and how it's, scheduled and mapped, and on the hardware. And it really depends. Is it a problem? It depends if you can hide it behind compute, or if it becomes exposed, right, and becomes a bottleneck. So a lot of my group's focus is on, how do we perform efficient hardware software co-design to minimize bottlenecks around communication and data movement, and how do we even determine if it's a problem, right? So we look a lot at mechanisms to kind of benchmark and simulate these problems as well. So some of the key research thrusts, are around just design space exploration. So co-design is challenging. You really need tools to understand the design space before you can actually start, optimizing for it. So my group works a lot on tools. The design space for, designing these like accelerators or these systems is very large. So my group also looks a lot at design space acceleration methods to navigate the search space. Data movement is a big challenge, both from an energy perspective as well as from a bandwidth perspective. In fact, one of the Ask Plus papers we have in a couple of days really talks about this bandwidth challenge for transformer models. So, we also look at like smart scheduling techniques and like designing the network fabric. And finally, right, like as we've all seen, at least in AI, like, it's a field that is changing very, very rapidly. So too much of code design is also harmful because, like, by the time you do that very extreme efficient design, like the model might have changed. So you also need flexibility. So my group kind of touches upon all of how I like to think about my group's research. So we're trying to do a very systematic, design of the entire acceleration platform. We start from the workload at the top, some objective that we want to optimize for, and some system configuration. Ultimately, we want to design some accelerator platform. We want to represent the design space. So you need to be able to represent the design space. You need to have some kind of a simulator or cost model for that. You need to be able to explore the design space. So we look at, mechanisms to do that. This is like a co-design loop that you need to work with. And ultimately, you come up with some optimized schedule or system configuration. And this is the entire space we work with, right? And so we've, like, over the last few years, I've been lucky to, publish across all of this space, right? So in terms of design space representation, we've done a lot of work where we've tried to understand the design space for both single accelerator systems and multi-accelerator systems. We've looked at exploration methods for design space exploration that use heuristics, that use, machine learning based methods like reinforcement learning, or optimization methods like genetic algorithms. We've also looked a lot at designing simulators and cost models, again, both for single accelerator systems and multi-accelerator systems. We've looked a lot at, scheduling and optimization. And finally, we've also looked a lot at actually designing flexible accelerators, again, both single accelerators and multi-accelerator platforms, right? And some of these, again, are papers that we'll present at Ask Plus as well. So this is kind of, I would say, more of the marketing pitch of my work, right? And this is really how I present my work when I'm going and giving, let's say, talks to different universities or to sponsors, right? But this is really, again, a top-down view, right? It actually gives an impression that I, have a very broad vision with several coherent pieces of work. But in reality, this is really a retrospective slide, right? And that is the thing I want to mention. In research, that's often the case, right? Reality is really noisy data points, right? We didn't really start off with this end-to-end vision with all of these pieces. You kind of, do interesting research, you come up, you find interesting problems, you have a, bunch of things you do, and then you kind of put it all together. And that is an art that you also learn as you navigate grad school, right? Some form of curve fitting is needed for a coherent story. I personally realized this quite late. That's why, as I mentioned, I was actually very intimidated by becoming a professor, because somehow I was convinced that, people who go into academia, people who are giving talks at these conferences, even if they're in industry academia, right? They kind of have this grand vision, and I just felt I am not that person, right? I mean, I've done a few papers, but how can I go and talk about like all of these things and, the future and so on? And actually, the very first time you'll encounter this, and you will actually have to do this, is your own PhD talk, right? bunch of, you have to kind of connect them together into a coherent story. A lot of times your thesis chapters might not be chronological with the order in which you publish things. So that's the time when you first face this. And again, as I'm saying, this is something that I do want to mention that, in reality, things are going to be noisy. You put them together into a coherent story, and there are ideas that do not pan out that will not even show up, right? So that's the broad thing to keep in mind. So that's why, at this point, like, work on a lot of things, be open, like work, and don't really worry about how all of this ties together. That's really, I think, what I wanted to mention with this slide. So what is my actual bottom-up journey, right? So my PhD research was on flow control for on-chip networks, right? So that was really my focus, right? That is already like a subset of the broad field of on-chip networks where, you have several different aspects people look at: topology, routing, router design. That's already, a subset of the kind of things people do in on-chip interconnects. People look at like point-to-point networks versus switch networks. This is, again, just a subset of just the challenges of communication in computer systems, which include both on-chip and off-chip. And this is, of course, just one subset of what you do in architecture, right? Like for many of you, like you might be looking at compute, memory, communication, storage. And this is still just yet a subset of like the broader computing stack, right? Where, especially where at ASPLOS, right? Like you'll find people working at all of these things here, right? Across the stack. So how did I kind of, go from here to now, as I said, like this talk that I give where I'm trying to cover all of this, right, in this entire stack. So that's really what I'm going to talk about. So the rest of my talk is going to essentially just, give you a snapshot of some of the papers that I identified that I've published over the last, decade or so, and some key learnings, and that helped me kind of, pivot and decide how my career was going to go from there, and end with some takeaways. So I'll start with Garnet, right? So this is a paper that was, I think, one of my early papers that I worked on as a co-author. So I was a very junior student. I think I had just started my PhD, and my lab mate Niket Agarwal, who's now at NVIDIA, was basically developing this simulator for on-chip networks called Garnet. GEMS was a very popular simulation infrastructure at that time from Wisconsin. GEMS eventually became GEM5. And so he integrated it into GEMS, and he was trying to basically publish this. And so I implemented some interesting ideas in Garnet, more as case studies to demonstrate the value of the tool. So I'm a second author on that paper. And while I was in grad school, like, even after Niket graduated, during one of my internships at AMD, actually, we helped integrate Garnet into GEM5. So I'm kind of a co-author on the GEM5 paper as well. So what's very interesting about Garnet for me personally is, well, it became one of the most widely used NOC simulators, and it has like lots of citations. It is, the Garnet paper has a lot of citations, and the GEM5 paper also has a lot of citations. Now, in terms of learnings from this, the reason I started with this was, of course, there is kind of the social value, right? Well, there's a lot of value to the community. If you do, do tools, you give it back to the community, it allows rapid exploration of ideas. But what about like personal learnings, right? So it's a huge learning experience. Like you basically learn the ins and outs of the system you're building the tool for, right? Which is actually a very, very nice learning experience. This is another thing I'll mention, right? It actually gives you a lot of credibility during job search, right? Whether it's industry or academia, the fact that you worked on tools is actually very, very rewarding, and it actually pays off. Why do I mention this? Because the challenge is that so this is something you'll all face. And again, that's okay. I think this is, so again, I was very disappointed at that time, and I've been through, through several tools we've done. But one of the things that, again, I wanted to emphasize was that it's disappointing, but it's okay. Like, publish them at venues that do value tools, right? Publish them at ISWC, ISPAS, like DAC Date. Like that's the conferences that my own research has expanded to, and we've published. And one of the things that, like, retrospectively I've also realized is that the citations of the tool and its user base demonstrate the impact, right? It does not really have to be an ISCA or ASPLOS paper in order for it to really have that. So that's something I want to mention, especially as junior students, as you kind of navigate a conference like this, see people with these papers. I know, like, at least it happened to me, right? You start kind of feeling like, oh, I'm just working on all of this engineering stuff. It's not really going to get in. What's going to happen, right? So don't worry. Like, again, do this work. It will get in, like, publish wherever it does get in. And then you can actually do other things to enable adoption, right? So open source the tool, create, document it, create a website, run tutorials. So that's exactly something we're doing. In fact, later this afternoon, we have 2 tutorials that we are running on 2 simulators that, my group has developed, Stone and AstraSim. They are, again, examples of something like this, right? Like simulators for the community. One of them is an IISWC paper, one of them is an ISPAS paper. But now in terms of the user base and impact, right, it's amazing, right? These are being presented at AskPlus and ISCA, right? So that's something I want to mention, especially for, those of you who work closer to engineering. And this is a very interesting learning for me from Garnet, right? That's why I wanted to start off with this one. So another interesting learning experience for me was my very first primary author paper, Swift. This was like a chip tape out. My advisor was planning to, collaborate on this idea. And I, again, as a junior student, essentially went ahead and implemented the RTL for a NOC. So this was a NOC. The idea itself was something that a senior student had done, was already a micro paper. And essentially, my job was to implement that in RTL, like create a NOC prototype. And then we were working with, collaborating with the group at Oregon State to try and, tape it out. So I had very basic, undergrad understanding of Verilog, but I was like very excited by this. I said, sure. So I learned Verilog and System Verilog along the way. It took, way longer than it would have for an expert, but successfully I implemented the NOC. The synthesis and backend PNR was done in collaboration with another group. So I was not really an expert in backend, but I kind of got to learn, again, that same idea of like just a high level of what needs to be done, like in terms of timing. The chip worked, but again, similar challenge. It was not novel enough for a circuits conference because there was not a lot of circuit level novelty. And there was not enough research contribution because, well, technically the main idea was already published. So this again was a paper that just took a long time to get published, finally was published at ICCD. So again, interesting. So this was again a phase for me, like again, being in your shoes where I was like, okay, I have this one paper where I've helped out a senior student that doesn't seem to be getting in its tool. I have this other paper, which is, just coming back as this is just engineering. And it was, it was time consuming, right? So implementing RTL, taking it through the entire flow takes time, a lot of issues. Again, less papers. But this is again where retrospectively I realized the value of this work, right? So a lot of credibility on the job market. So when I was going up, so as I mentioned, I initially interviewed in industry, right? So they were, of course, the traditional hardware companies that interviewed me, like the Intels, NVIDIAs, and AMDs. This was a time when, Microsoft and Google were still they're still cloud vendors, but now we all know they do hardware research. So this was kind of before it was publicly known. So it was very interesting for me. I applied to Microsoft Research thinking, well, I'll apply, but they probably won't even interview me, right? They will interview more systems folks. But I got an interview call, and then when I was interviewing, they were like, oh, we really saw on your CV that you have RTL experience. That's actually something very valuable for us, which was very interesting for me because that was the time they were actually starting out their FPG effort, right? So that now, of course, was public. After that, they integrated FPGAs throughout the data center. So it was very interesting for me, like for this one chip that I did, had a tough time getting it published. After that, I didn't do any, anything. I didn't really want to do anything with that. But that was what, suddenly made me attractive to Microsoft. Google contacted me as well. I didn't end up interviewing. I had already accepted an offer. But now later, I was told that this was actually, the TPU team, which was basically, again, was not public at that time, but they were doing ASICs. And they were like, hey, we have somebody who has ASIC experience. So again, one of those things, again, where, it's interesting, like connecting the dots that, it's fine. Like do good work. It'll pan out at some point. Another thing that, of course, one of the other learnings was that once you do a lot of this kind of hardware design, it does make you cynical, right? You realize that a lot of the models that we use are not very accurate. Like once you start doing low-level circuit design, you realize that even small things like the area and power will be determined by a lot by the frequency you set for synthesis, right? So if you want to make timing at 2 gigahertz versus 100 megahertz, for 2 gigahertz, the tool will start making the standard cells larger and larger area will go up, right? So a lot of the, in fact, area power models we used within GEMS and GEM5, I realized are actually not accurate. So it was an interesting, again, learning experience that helped pave the way for other things I did in future. So now moving on to my core PhD work. So I'm still kind of in the journey on my PhD papers. This was my main thesis work, this network on chip design called SMART. This was my final paper that was at HPCA 2013. It also won topics. So here the question was, we were trying to understand what limits us from designing a single cycle network. Like I want to design a network that takes a single cycle anywhere on chip. So the question was, well, is it the wire delay? Turns out it's not. You can actually, you have repeated wires, and as long as you have repeaters at a certain spacing, wires are actually fast enough for, very fast traversals on the chip. The challenge is really routers, right? Ultimately, you have to send your data through these routers along the way. And even if you have no other traffic, at the very least, you'll get latched at the input port of the router and then at the output. So you will end up taking, in this very simple example, 9 cycles, right? In the best case, no traffic, nothing else, but you're going to take 9 cycles. So of course, you can't really design all-to-all like, dedicated networks unless you're doing some ASIC for a specific application. This is like a general purpose multi-core, and routers are required to share links. So how do you so you now have this conundrum where wires are, fast enough, but ultimately because you're trying to design the shared network, right? Think of like a road network that you're designing with things are shared. You obviously have traffic signals that you have to stop. So SMART was this idea where we could try and get both. So essentially what I did was, augmented all of these routers with these bypass paths, which ultimately, like the idea was you could, if you wanted, completely bypass the routers asynchronously, like not getting latched, creating a long multi-hop path through these repeated wires and get latched at the very end. And so the idea was, microarchitecturally bypass these paths with these clockless repeaters and compete for and reserve a sequence of shared links cycle by cycle. So you would dynamically create these repeated links or smart paths between any 2 routers. So essentially the idea was, if I have traffic going from here to here, this is a single cycle path, this red one, this purple one, and this blue one. Then I have a single cycle of reconfiguration of these paths, depending on the application or whatever the coherence protocol demands. And now I have a different set of single cycle paths. And the only reason you ever stop is if there is explicit contention. So in this case, the blue and pink flow are both wanting to use this link. So I've not physically added more links. It's still, the shared links. In that case, the blue flow stops while the pink one continues, right? So that was the idea where, can we do this? Can we create, let's leverage the fact that wires are fast enough. We enable the NOC to have these bypass paths, and then we have a flow control mechanism to kind of very quickly create these paths. It's almost like doing very fast circuit switching, but without creating a circuit and getting an ACK. It was actually trying to do it very opportunistically. So my learnings from SMART actually, and this is where I really have to credit my PhD advisor, Lisha and Pei, were really about, I think this came across more as a very, very cool thing where, like, our group was already doing a lot of NOC research, trying to make NOCs faster and more intelligent. And Dishan's questions to me were, well, can we design a network with intelligent behavior at each router, right? Let's it not just be a dumb router that's just transferring packets, let it do more than that. And let's keep pushing on this, right? Can we then design a router that takes a single cycle, even with this intelligence in it? And then can we design a network that takes a single cycle anywhere, right? So not just within a router, as I showed, but actually across multiple hops. And to top up all of this, can we do all of this dynamically, right? So like you could always still set up these circuit switch paths if you knew what the workload was, but can we do it dynamically? And so my kind of quest in grad school was to answer yes for all of these, right? And it was amazing. Like the journey was amazing to try and do this. It was a really, really cool idea. And obviously, right, it was a very cool paper. Like, it got me my industry job and then my academic job. So it was a really cool idea. Another thing that I think was a learning for me, which again, I think this is a very interesting learning that is useful, is like, I think it allowed me to really understand what is the best you can achieve in any system and keep pushing towards that ideal. So one of the things my advisor would always ask me is, well, don't just tell me this is, 10% better, 20% better, 3x better, right? Like, tell me what is the best you can do and how far it is from that. I think that was a very, very nice learning experience, and something I, again, want you all to keep in mind, where like really try to understand what the system limits are and how far you are. And then, of course, you might not be able to achieve it for various reasons, and then try to understand how to optimize for those. And what was also very useful in that context was we learned that, especially in the context of on-chip networks, new circuits and new technologies could actually allow you to do both 1 and 2, right? So this cool idea of trying to push the limits, do a lot of things dynamically, and try to get to the limits were things that new circuits could allow you to do, or new technologies could allow you to do. So there were some explorations we also did, which I'm not going to talk about, where we tried to see, oh, what if I put photonic links here? What if I do this and that? Right? And there was some low swing signaling we did. So a lot of interesting ideas to push to the limit. So this is great, right? So yes, you can design cool things and push things to the limit. So that was the learnings from, I would say, a more academic hat, right? But the reality check was actually, this is where this was more, I would say, courtesy my interaction with the industry, right? As I presented this work right after I graduated, was cool ideas are great, but they might not be very practical for industry. So this was kind of an anti-learning for me, where for industry, and this is actually a very interesting analogy, and I think Bill Daly said that at some point, I ran into him at a conference about vitamins versus painkillers. He was like, well, in industry, if there's a pain point, they want painkillers. They don't want vitamins, which are just good for you, right? So this is something that for many folks who work in industry, they've kind of, gone through academia and then gone to industry have said this, right? So ideas that are good enough make it to products. They don't really have to be the best, right? That's one interesting kind of learning that kind of complemented the learning I had earlier. The other thing was also that just pushing for ideal may not make sense, because that might not really be the bottleneck in the system. That was especially true for me coming from the, the myopic view of on-chip networks, where even if I design a network that takes a single cycle, it might not make a huge difference in overall application speed up, because at a lot of cases, especially at a data center scale, you're dealing with like microseconds of slowdown because of things in the software stack, right? So just like you went from like 10 cycles, 10 nanoseconds to 1 nanosecond is not going to make that much of a difference. It will in some cases, but not in all. So this is another thing that I felt I learned like at the end and after my PhD, which is also something I want you to keep in mind, where again, it's great to kind of be in, be very focused, try to get the best out of the whatever component you are optimizing, but do remember it's part of this larger system. And in that sense, it's good to kind of critically ask, how much you want to push that, or are you just like, it's not really going to help in the larger system. That's another thing to keep in mind. So this was my PhD journey, right? So Garnet, Swift, Smart, and then I was at Intel, as I said, for a year, and then I went back to MIT, and I was basically doing my job search, and I was done with my job search, and I had some time, and that's when so Joel and Vivian at MIT were working on the Iris chip, and of course Joel knew me very well, like he was my manager when I was at Intel, and he also was on my thesis committee. So he said, well, you know what? We're trying to design this NOC for this chip we are designing for this emerging class of workloads called CNN. So this was like right after, like this deep learning was just taking off. So people had started hearing about convolutional neural networks. It wasn't, but at least in the architecture community, not as pervasive. And he said, oh, we want to use your smart NOC and try to put that into this Iris chip. And so essentially to design this NOC, this was the traffic pattern they described. Well, you have these filter weights that will have to go across these P's like this. There's these input activations that have to go diagonally, and then you have to collect these outputs, right? And so now to start designing this NOC, my job was, well, okay, I have this very cool NOC, smart NOC, does, single cycle anywhere. Does that notion work? It does. Here, like the P's are really small. Like I was already talking about trying to cross multiple hops for a multi-core where the cores are really big. But when you have these really tiny P's, which is just a multiplier, adder, and some buffers, you can actually go like, across this entire row within a cycle at whatever, right, gigahertz very easily. So this was possible. So you didn't really have to design something like a systolic array with like, store and forward and put a lot of latches. You could actually go and do it very quickly. But you didn't really need like sophisticated routers like I had in the smart NOC, because this was not a many core. It was like the traffic pattern was a lot more deterministic. So we ended up designing something that eventually like looks more like a glorified bus with some interesting, repeaters. But the idea was really the same, like single cycle across all of these sender weights activations in a cycle. But you don't have to now and do a lot of dynamic arbitration because the pattern is more deterministic. So my learnings from Iris were actually, I would say, very, very interesting, right? So one thing that I learned was I mentioned my experiences with Smart, where, I presented, people were like, NOC is not really a bottleneck. It's fine, just 10% of the multi-core area, not really a bottleneck in the system. But when I'm designing accelerators, the on-chip latency matters a lot, because it's not a traditional core where I have a lot of mechanisms to hide delays, right? It's not like I have caches and out-of-order processing where I have a memory access, it's fine. It can take its sweet time. I can do other things. Here, you're just stalled. It's like really like a data flow machine. Like you have, if you don't get the input and wait, you'll just stall, right? Waiting for it. So the NOC is much more important. both from a latency perspective and from an energy perspective, because again, I don't have expensive, caches and speculation taking up energy. It's really just the multipliers, adders, and the interconnect that's taking up energy. So this was good. The traffic is, however, much more deterministic, which basically meant that, for accelerators, like I basically need to think about NOx, but I have to maybe, shift my thinking and try to start thinking about designing something that's more application specific. So this actually was, I think, the first time. This was kind of, end of my PhD, before I was about to start my academic career. This was when I was really able to, expand my scope, right? Going from just somebody who was doing NOx and flow control to now starting to think about communication broadly. And again, I do have to thank, I think, as I was, talking to different people, I think I remember this was, I think, Margaret Martinosi, who I was like, oh, I'm starting my career as an academic now. And, NOx, is that really what I should be focusing on? And she said, why are you thinking of yourself as a NOx person, right? You're somebody who's optimizing communication. It was a very simple line, but it just suddenly made me realize that, yes, right, again, the same point. Your PhD might be on some piece, but really think about the bigger picture where it fits. I was somebody who was optimizing communication. I happened to design NOx for many cores for my PhD, but ultimately, if I start thinking like this, then it kind of, broadens the scope of the kinds of things I do, right? And I can do. So this allowed me to now start thinking a little bit more holistically. So when I went to Georgia Tech, one of the first things we did was this design called M.E.E, which I would say really kind of, started off from where what we had done with Iris, but now was thinking about communication in an accelerator in a more, systematic and generic manner. So, like in a chip multiprocessor, I kind of have all-to-all traffic, like any core can talk to any core depending on how data is mapped by the coherence protocol. Or if I have an MP sock, it's really, static. So I can design an application-specific NOC. In an accelerator, I still need something that's more general, because it's not like I'm running just a single, ML model, right? I'm running diverse models. But at the same time, I don't need something that's like a full-fledged generic NOC like a multi-core, right? So we started trying to understand the kinds of communication patterns inside these accelerators. We realized that they kind of fall within this realm of, few to many, like, few of these buffers sending data to many of these processing units to distribute operands. And then you have like a many to few kind of a flow where you're trying to collect outputs, maybe doing some reductions along the way, right? So we kind of abstracted whatever the model and mapping would be into this thing about, we need some network that can handle this few to many and many to few. And these are kind of different phases of operation, right? Like when you're distributing operands or collecting things. And so this allowed us to now start thinking about, designing a very application-specific NOC for these accelerators. So M.E.E was this work we published a few years ago at ASCLOS. This was also a Topics Honorable Mention, where it kind of started thinking about accelerators as these building blocks where I have multipliers and adders and buffers. And, these are just like, again, instead of full-fledged NOC routers, the ones I had used in my PhD, I'm going to now start thinking about these very tiny switches. Basically, I strip out all the smarts from a router and I just keep the very basic functionality. I just need some muxes, some buffering. I don't need like, fancy routing or arbitration. And then we kind of, created a specialized topology for distribution of operands that allows us to do reuse. I'll go through this quickly. Again, this is a full-fledged talk in itself, but I just wanted to give you a glimpse of the kinds of things M.E.E had. So a linear network, collection network. So this was essentially a set of different designs coming together. So a distribution network, a local network, and a collection network, each of them optimizing for different kinds of data reuse inside the operator that I've mapped, right? And these were, again, not full-fledged NOC routers, but micro switches. So my learning from M.E.E was, again, that, now that I'm starting to think about communication in accelerators, let me kind of think about these very specialized distribution collection NOCs. And it kind of led to this notion of this communication-centric accelerator design. So rather than, again, general purpose NOCs, I'm trying to do specialized NOCs, but they are still, somewhat flexible and configurable for the use case. So M.E.E was targeting dense CNNs. Then we did Sigma subsequently at HPCA 2020. This was targeting like sparse gems. And then we have a paper, Flexagon, at this ASCLOS, where we're again targeting sparse matrix multiplications, but we have a lot more flexibility in the kinds of data flows you support. One of the other learnings here was that if I have some kind of flexibility in the NOC, in a traditional multi-core NOC, like the NOC is kind of just completely hardware managed, right? So there is no control of the NOC from software, but here there is probably an opportunity to start controlling this communication from software as well. So this kind of was my foray a little bit into compilers and trying to see, well, can I actually, control how things are moving inside the accelerator from software? Which then led to this question, well, okay, I really want to control this communication inside. So, again, just to kind of recap, right? So far, I was completely abstracted out from what the workload is, right? I was just trying to design a NOC that was fast. Now we're starting to look at workload behavior and we want to optimize the NOC, understanding what the workload behavior is. So we really need to try to understand the relationship between the algorithm being run and its traffic. So this kind of allowed me to expand my scope even more, right? So it's not just about communication, but now I really want to understand what the algorithm is, how it is compiled down. Again, this is an accelerator. So some of these intermediate layers don't really apply, but what's the algorithm? How do I compile it down to my accelerator and control the communication and then design the hardware, right? So this kind of allowed me to expand the scope even more. So then we went ahead and did this work called Maestro. This was a paper at Micro 2019. It's also a topic. So again, without going into details, this was really trying to understand the relationship between the workload that I'm running. Let's say, I'm running some CNN or some operator with a certain shape and size. How do I think about systematically, tiling it and scheduling it? What are the implications on data reuse? What are the implications on the traffic patterns inside the NOC? And then, subsequently, how do I design this? And so then we also created an analytical model called Maestro for estimating the reuse and performance from this. So Maestro was again very interesting from a learning experience, right? So the first thing was that it exposed to us the importance of design space exploration. So, it kind of taught me that a precise taxonomy of design spaces matter, right? So instead of like individual design points that we're trying to create, if we can very formally describe the entire design space for an accelerator, includes both the hardware configurations and the software mappings, then, there's a lot of opportunity to optimize. And it also meant that design space exploration is actually very, very crucial to get to the best design, right? So this again comes to that point I meant earlier about, my learnings from grad school about pushing to the ideal, right? So what is the best I can achieve? Ultimately, I have some processing elements and memories and, things connected together. What is the best I can achieve? For that, I need to understand what are all of the possible choices for running the workload on that accelerator and all possible traffic patterns. And then I kind of search through them and identify the best, which either optimizes for performance or energy or performance per area, right? That's what it lets me do. So pushing to that ideal. And design space exploration is then that point of what led my group to start looking a lot at that. We started looking at cool design space exploration methods, like using reinforcement learning, genetic algorithms, and so on to do this kind of DSE. My other learning from Maestro, again, which kind of comes back to a point I mentioned, the same experience that I had in grad school, right? So this paper took several years to get published. And again, it's natural to get cynical, but the challenge again was this was like a tool. And I mentioned already, right, about like the challenge in getting tool papers accepted. And here we focus a lot on like, positioning this work. And finally, it was positioned more as a paper that was on understanding the design space, and the tool just happened to be an artifact that comes out rather than being a tool by itself. So this was an interesting learning experience. And again, I think my point here is that, when you're in this phase and you will be in the state through grad school where papers are not getting in, try avoid getting too cynical and just blaming like the reviewers didn't read the paper, right? Like really focus on what is the best way to communicate your ideas so that, you can convince the community that this is valuable. If it's good work, it will get in. Like that's kind of like, just be persistent, just be patient, and like just stay at it. And as I said, like, don't just get fixated on I have to get this published at this one conference and not anywhere else. The other, again, learning which kind of mirrors what I mentioned with Garnet was about adoption and impact, right? So the value of, open sourcing your tools, tutorials. We did a tutorial on this. We started a whole tutorial series. We did one at ISCA 2018. This was the first one, then a few others. This actually led to an invitation to us to write a synthesis lectures on designing accelerators. It also led to invitations to me to, collaborate with industry and Department of Energy. Right? So again, was an interesting thing where, do good work, get it out there, and then things will follow, right? So don't really like get too worried about what is happening. So just wait, right? Be patient and things will happen. Just kind of do your best. And again, do your due diligence in making sure that these things get out there. So very quickly moving on to a couple of last things. So one other piece I wanted to mention, this is not a paper that I usually talk about, but it was again an interesting exercise for me. So this was a conversation with somebody I ran into at the DATE conference, right? So this is not a conference I usually attend, more an EDA conference. And I was telling him that, hey, I work on NOCs, and this was somebody who did FPGAs. And he's like, oh, well, it'll be great. Like, I really like this idea of trying to bypass routers. Well, on FPGAs, we have a lot of these LUTs and we have these wires. Like, can we do something like that on an FPGA? So we started talking, and this was a paper we published, which is, I mean, one view is this is like the smart NOC on an FPGA, but it was really again trying to leverage like do bypasses across several lookup tables to essentially not go to the FPGA fabric every time and enhance the frequency of the FPGA. So this is just some analysis from that paper. But again, it was an interesting learning experience for me on, again, trying to take the same idea, like, in one case, we had applied it to something like DNN accelerators and try to strip off the NOC. Here, we were trying to apply it to FPGAs. I realized that wire constraints on FPGAs are extremely different from ASICs, right? And area costs also go up kind of as a step function, because as soon as you need one more LUT, right, like the area kind of just jumps. And it is possible to optimize FPGAs by cleverly engineering the LUT and wire usage. And again, you need to rethink interconnect architectures if you're applying that same idea to a different system. And finally, more recently, we've started, expanding the scope even more, right? So why limit to just a single accelerator and interconnects within that, right? Let's try to think bigger. We've started looking at, multi-accelerator platforms, like, the kinds of things, let's say, the industry is building. So cloud TPUs, NVIDIA DGX, Cerebras wafer scale engine, they're all like examples of, several different accelerators connected together by different kinds of interconnect technologies. And again, the same thing, right? There's a huge design space here that one can explore. In fact, this is the tutorial that we're going to be doing this afternoon, if you're interested, on AstraSim that models this design space. And here again, I had very interesting learning, right? So I'll again kind of the thing I mentioned in the beginning, I'm not a systems person, right? My PhD was very low level microarchitecture circuits, right? And how am I kind of now working in like these large scale systems? I think this is where I feel this is the power of abstractions, right? Like ultimately, like from a 10,000 foot view, this large scale distributed ML platform is really like a many core connected by a NOC. It's just that, so the key notions of latency, bandwidth, like these things remain the same. It's just constraints are different, right? So as long as you, again, right, you don't really need to be, as I said, like a deep expert on every topic, right? As long as you understand the basics, the fundamentals about latency, bandwidth, and you understand the constraints, your skills are transferable, right? So I was able to now apply the same skills that I had learned for like on-chip network design to more like system level network design, and kind of optimize accordingly, right? And the other things that was interesting in this work was the benefits of scale, right? So if you're operating really at scale, again, as I mentioned, this notion of shaving off 1-2 nanoseconds doesn't really make sense, right? So a lot of the analysis can really be like this big O analysis, right? So I'm sending these very large, I have these large models, they are sharing these large gradients, I'm sending these large messages. You can really abstract the latency as, you're just limited by the bandwidth on the link. So you can get that delay, right? It's not going to be accurate, but in a real system, it might be off by a few nanoseconds. But again, we're talking, as I said, at microsecond scale here, right? So this kind of thing was interesting, where you can now start doing more first order analysis. So again, it's good to understand when you can do such analysis, but there's also, of course, other challenges of scale, right? Like in an on-chip network, we were able to do very detailed simulations. Here, like in a large scale system, that's much more challenging. Emulation is challenging. And in some cases, software stacks can play a very, very big role in overhead as well, in terms of overhead as well. So finally, through this, I want to talk about some key takeaways and learnings and just summarize, right, the things that I talked about, right? So one takeaway again for all of you is, there is tremendous value in engineering and building tools. That's something I want to reiterate. There's also tremendous value in collaborations across the computing stack, right, to expand your scope. So start saying yes, right? You are not yet at the stage where you have to say no. I'm at the stage where I've started learning how to say no to things, but, be open, right? Like this is the stage, this is grad school, like go say yes, like, participate in different contribute, right, in some manner to different things, right? So again, same thing, right? Continue working on your main thesis topic, right? But you be open to helping out lab mates, friends in different research groups to enhance your portfolio of papers, or at least learning, right? As I said, that will go a long way. be open to remapping your ideas, right, across different aspects of the system. So again, this is where I'm mentioning that you've done some idea, you're very passionate about it, you've published a paper on it, but don't get very dogmatic that that's really the way it has to be done. Be open to seeing what aspects of that idea can be applied in different systems. That will really kind of amplify the impact of that idea. So that's something I really want to emphasize as well. And again, this is something I want to caution you about. Like if you've not heard this term escalation of commitment, like to read, we hear Adam Grant's podcast on this. So this is the idea where if you're kind of, working on something, you've invested a lot of time, even if it's not panning out, you're like, well, I've already invested this time, you kind of keep at it. So persistence is good, but at some point you need to realize that this idea just is not making sense and pull out, right? So that is also something to keep in mind. This is another thing to keep in mind in grad school. Like otherwise it's very easy to, have 1 or 2 years, just go and, nothing has come out and you start feeling really bad. So just be cautious. So again, that's why also I feel like, be open to a lot of things. And so what that also means is even if your main idea doesn't pan out 1 year later, it's not like you've done nothing, right? You also contributed to other papers. So that certainly helped me, as I said, like I had second, third author papers that were also there. And even if my main paper took a while, it did not really hurt my overall CV. So just reiterating, tips on expanding your scope, right? So a lot of the things I mentioned, you might feel, well, but I'm a professor, right? I can really decide, hey, I want to work on X, Y, and Z. How do you do that? You're a grad student and your topic in some sense is heavily dictated by advisor, right? But that's what I'm saying, right? So just that does not mean you cannot expand your scope beyond what your specific research topic is, right? So understand problems of other students in your group, right? Talk to them, like see if you can help them out, like whether it's in your group, whether it's in your university, right? Attend thesis defenses and seminar. This is something I'm gonna really like. This is something that students don't end up doing a lot unless their advisor really asks them to. But I found this very valuable, and so go attend talks, go attend seminars, go attend things that go beyond your own area of expertise. Right? There's always going to be some learning. Sit through courses. Again, you probably don't have the bandwidth to take a lot of new courses. You're prioritizing research, but sit through different courses. I mean, nobody minds if you're kind of sitting through different classes, right? This will also help you expand your scope, right? And work on and understand a lot of things. And again, practice elevator pitches of your work, right? Talk to different students working on diverse topics at ASPLA. So these already the organizers have enabled that at this lunch, but I really want you to do that. So finally, I'll end by, just kind of quoting from Steve Jobs, like, and I think this is something that I heard his, like, if you've not heard his Stay Hungry, Stay Foolish, talk, please go and do that. It's amazing. But now, after I've spent a few years, again, I don't claim to be, as senior as a lot of people who work in this domain, but this notion has started, like, I'm understanding what he meant by this notion of, connecting, you can only connect the dots looking backward, right? So that was my attempt today. I kind of tried to connect dots through a lot of things I did and see, some of the key learnings. And I really hope that, some of these learnings stick with you guys. And so again, stay hungry, stay foolish, and like, enjoy ASPLOS, and thank you all. And I'm open to questions.
Thank you, Tushar. This was an awesome talk. Any questions from our audience? Can start with one. So is there anything that kind of got stuck all the way from the beginning of your PhD to today that you keep seeing again and again and again? Like one thing that kind of comes back as a negative or positive?
Yeah. So I think I would certainly say in my case, like tools is definitely one of those. I said, this was there through my PhD through now, right? So working on tools, like working on these engineering artifacts, and then kind of struggling with the right positioning and like the right venue to get them published. That is something that is stuck. So as I said, like retrospectively, I saw the value of that. So I continue doing that even in like, my career right now. But I do kind of feel bad for my students where like, well, this just doesn't seem to be getting in, right? So that's something that has stayed, but that's where I've kind of now learned to navigate around that and see, what's the best way of decoupling where it gets in from what's the way of, getting it out there and in terms of adoption and impact via tutorials. Yeah. Yeah.
From the audience?
Yes.
Thank you for the talk. I guess I was just wondering, so I like the description of your methodology of how like the research process itself looks. Do you have kind of a similar methodology for how you, once you're at a point where you're ready to like start looking backwards to start like, putting the steps towards getting your dissertation together? There's a methodology for how you start.
That's actually a great question, right? So the question for people online is like, what's kind of the mechanism of starting to collect the dots, right? Connect the dots looking backwards. So I'll kind of walk through how I did it for my own PhD work, right? And again, a lot of it was, I would say, just with discussions with some fellow lab mates, right? So at that point, all those papers were very decoupled. Like one was on some chip tape out for a knock, one was on some coherence related, like optimization to broadcast, one was on some micro, and the papers venues were also very disparate. They weren't all architecture. One was at an EDA conference. So you kind of then start drawing bounding boxes, right? So at the very least, they're all on chip networks. Okay, that's fine. So now you start coming in, what is the metric I'm optimizing for? So even though, of course, we optimize for multiple things and everything, right? In the paper, you say this is great at energy and latency and blah, 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 right? So ultimately, it was like, somehow it really seemed to be optimizing for latency. Like this one tried to do a single cycle within a router. This one tried to do a single cycle for broadcast. So we kind of, so narrowed it down to, some key piece that is common across all of them. And then like, that's one way of trying to see what the overall scope is, right? So that was at the knock level. Right? So now the way I do it is, okay, ultimately, all of this is optimizing communication, right? So even if the paper itself is going to be a pure accelerator paper, right? I'm not claiming it's just so the papers, none of these papers say, hey, this is a new knock for an accelerator, right? It kind of is not really true. And it kind of even diminishes what the paper is about. But I know the way all of these connect is they're all really about optimizing data movement. One is at the hardware level, one is from the software level. So just try to find some common theme, some metric that is common across all of them. And kind of let that marinate, discuss it with people and see. That's one way of doing it, yeah.
Thanks for the talk. I was wondering, has there ever been a time where you worked on a project and you found out a good way through it that other groups or that you didn't know of or was working the same thing? And if so, what happened with you about it?
That's a good question. So I think it happens a lot. And in fact, I think especially if you're working in a domain where a lot of people are working on, it happens a lot, right? So in my PhD, it was NOx, and NOx was something a lot of people were working on at that time. And now, of course, it's ML accelerator. So I would say that it's, so it depends. In some cases, what's happened is, well, it just, you work on something, somebody else works on something, it's somewhat different, like, both works get in, and at some point you kind of, connect and see how, what is common and so on, right? In some cases, you are unlucky where like the other work has gotten in and it's maybe you just solved the exact problem you were solving. And that's actually where this thing about, that's why I was saying, like, that's where this helps, right? Not being very dogmatic about this is exactly my idea and now nothing works, right? Think about which aspects of it still work. And I have a very interesting example of again, not my example, but one of my lab mates in my grad school. He was working on something related to reliability, and he saw like on NOx, and he saw the exact same idea in that paper kind of published. And I remember he was very upset. And so then my advisor and they worked on, again, repositioning. So they kind of thought, well, you know what, let's see if this idea that he was working on can be more generalized. So it became more of a methodology for doing reliability on NOx, as opposed to while the other paper, which they were like, hey, so there's this other work, but that's just like a single design point, and we are now more general, right? So I think it also in some cases becomes an opportunity for you to rethink. If your paper had A, B, C, D, X, like 5 things that it was good at, if 1 or 2 things are already now published, maybe like push on the other and see if you can expand there. That's one thing. And the other thing that sometimes happened is, well, it turns out that the other people who are working are such close colleagues and friends that, you just literally had a call and be like, hey, we're doing the same things. Maybe we should just join forces and write a bigger paper. And again, from a student perspective, I will say that when something like this has happened and my advisor did decide to do this, if something like this happens, we kind of also decide, well, you know what, maybe it'll just be, the 2 students from the 2 groups working together with, as joint authors or something, right? So because I understand that feeling as soon where suddenly, I don't want to just lose out all of the work I did. So there's different ways of navigating this. And yeah, I mean, all of this is fine. Like, yeah, it works out at the end. Yeah.
Any other questions? Yeah. So in the previous slide, you mentioned that at some point you might have to decide that something is not running out. Maybe we can change that.
Yes.
What's your insight there? When do you decide? How do you decide? Any more information?
Yeah, no, that's a good question. So I will say that to be honest, have not been very good at that, right? Like, you do feel, I mean, at some point you're very passionate about it and you're like, so I kind of typically follow the model I mentioned for the previous answer, where I'm like, okay, it's not panning out, but I still really like this idea. Let me see if I can reposition. So that's the thing I followed. That's, I think, something I've very active. I'll just try to reposition it in a way that it applies, right? In that sense. So, and a lot of cases I said, like, it's worked out where this is now more general, or it works for a different application, or it works for a different domain, and so on. The other thing that's now happening to me is some of this just happens because I work on a lot of things. If something is just not panning out, it just automatically just gets dropped, because let's say that student also has started working on something else, and at some point we're like, do we really want to go back to that? Maybe, it's fine. It's okay to just let it go. So I don't have a very strong